morning, everyone. My name's John. I'm going to be talking about going to the moon. So my aims and objectives for today are to examine some of the challenges in launching a rocket to the moon. And hopefully at the end of the session you'll be able to recognise some of the challenges that they faced and explain briefly how some of these challenges were overcome. I'll have a quick whip round the room. If you want to just briefly introduce yourself and just tell me what kind of previous knowledge or interest you've got in this kind of subject, really. Dan, if you...
Hi, my name's Dan Andrews and I've got plenty of space between my ears.
Excellent. Brilliant.
My name's Brendan. I quite enjoy chemistry and science, so quite
Right. Okay. Dan?
My name's Daniel, and my favourite wallace and grommet is when they went to the moon. I thought it was made of cheese.
Yeah. Yeah, it is actually made of cheese. Tim?
Yeah, my name's Tim and I do like science.
Great.
As a whole.
Okay, hopefully you can help me out. Any technical questions, then ask Tim.
Yeah, I'm Alan. I also like science, specifically cosmology and physics, so I'm kind of into rockets a little bit.
Okay, so half the audience will be on my side, hopefully. So, JFK. So he was instrumental in getting America first to the moon. What was the motivation of it? So I've got a quick video just explaining why go to the moon in the first place. Over to JFK.
And they may well ask, why climb the highest mountain? Why 35 years ago, fly the Atlantic? Why does Rice play Texas? We choose to go to the moon. We choose to go to the moon. We choose to go to the moon in this decade and do the other things. Not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win, as the others do.
So, because it's there, and because it's hard. So, a little challenge for you guys is you should have a bit of line paper in front of you. So, this is a very, very long speech from JFK. Can't fit it all in my 15 minutes, unfortunately. But I have another little snippet of it which explains, in JFK speak, some of the challenges that they have to face. So, if you can all write down at least 5 things that JFK says that are a challenge. Roughly.
We shall send the moon 240,000 miles away from the control station in Houston. A giant rocket, more than 300 feet tall, the length of this football field, made of new metal alloys, some of which have not yet been invented, capable of standing heat and stresses, several times more than has ever been experienced, fitted together with a precision better than the finest watch, carrying all the equipment needed for propulsion, guidance, control, communication, food, and survival, on an untried mission to an unknown selection of bodies, and then returning safely to Earth, re-entering the atmosphere at speeds of over 25,000 miles per hour, causing heat about half that of the temperature of the sun, almost as hot as it is here today, and do all this, and do it right, and do it first, before this decade is out, and we must be bold.
Thank you, JFK. So, if we run around the room, Dan, have you got one challenge?
Yeah, so it's
that
safe back to Earth.
Return safely. Yep. Excellent. Brendan?
They need to invent new alloys.
New alloys. So, yeah,
They need to.
they were designing a rocket that they couldn't physically build. They didn't have the technology to build at that time. Dan?
The distance, 240,000.
240,000 miles away.
Yeah.
What's that in bananas? Tim?
The speed at which the vessel is expected to travel.
Yep. What was that speed?
Offhand, I couldn't tell you.
So
I know it was very fast.
25,000 miles an hour. So
Yeah.
coincidentally, the return speed is the same as the speed they need to go to get there. Alan?
An untried mission to an unknown destination.
Yeah. So unprecedented. No one had ever done this before. So we use this one. It should work. There we go. So these are some of the challenges. So yeah, the distance, the size of the rocket, over 360 feet tall. Special alloys, yeah, we mentioned that. Precision engineering, the vast amount of equipment they need to take with them as weight, and the speed they need to go at. Temperature on return, half as hot as the sun. And be first was the primary goal. So what I'll be focusing on is the size of the rocket and the speed that it needs to go at. Okay, why is the Saturn V so big? That's not quite to scale, that's a Lego model. This is the actual scale. So taller than the Empire State Building, Big Ben. If you've never been to Big Ben or the Statue of Liberty, there's a banana for scale. So why is it so big? At the top there, you've got the little capsule and the little lander in there. So why is it so big? What's the rest of it?
Lots of fuel.
Fuel.
Supplies.
Absolutely.
So you've got a lot of stuff.
So I've got a
I get really well.
little group task. I did hope you were going to build a rocket, but we're going to have to settle for post-it notes, unfortunately. So I just need a volunteer that's good at drawing.
Well, I'm not good at drawing, but if that, I don't mind doing
Do me a
it.
favour. Draw your best rocket. Try and make it nice and big to fill
Oh,
the page.
your best rocket. Right, okay. Could be really dodgy this one.
You've got a dodge rocket, alright.
Right, I'm gonna do right. I'm gonna use that.
Nice. Just like Elon Musk's Starship. Perfect. Excellent. Okay, so payload. So the three guys in the capsule.
Still need me?
Yeah, you'll get involved. I'll give
Right,
you some
I'll wait here then.
post-it
I'll
notes.
step aside.
So we've got the weight here that we need to lift to the moon. So one, just for argument purposes, one block is 1 ton. So if we say 1 ton of mass requires 2 tons of fuel. So if you want to take post-it notes and build your rocket. So if you want to come up, how much fuel do we need for the 1 ton of weight?
I don't need two.
2, okay, so we'll stick 2 post-it notes on there. Okay.
He's doing it. Grab the bottle.
Any way you like. So there's our 2 tons of fuel for our 1 ton of mass. So, is that enough fuel?
No, because now I've got 3 tons to lift.
Exactly. We've hit the nail on the head there. So our rocket has suddenly got heavier. We need fuel for the fuel. So we've got a 3 ton rocket there. How much fuel do we need?
6 more tons.
6 tons. So let's make sure we've got 6 tons of fuel.
Some more post-its.
Yeah, yeah. So donate your post-it notes. Cheers, Alan. Thank you. So it's 1, 2, 3, 4, 5, 6. So you get 6 tons of fuel plus the weight. That's 7 tons.
So we need 14 tons of fuel.
We need 14 tons of fuel. So keep going. So can you see the problem?
Yeah, yeah. It's never ending.
It's never ending. It's a bit of a paradox. You need fuel for the fuel for the fuel. We keep going and going and going. And you end up with a curve like that, diminishing returns as you keep going. So how does a rocket get into space then?
Splits into parts, drops them off, and
Yeah,
Burns it,
so-
fuel, makes it like burns fuel.
burns fuel to make it
So
lift as it goes.
I don't know what his name is, where's Wally or whatever. So what's happening to his boat as he chucks rocks out the back there?
It's lighting.
It gets lighter.
It's
So
moving.
what gets ejected out the bottom of a rocket? Fuel. So the rocket, as it's going up, loses weight, and that's how it gets to orbit. And What else does it do? How else can it shed weight? I think you mentioned it, Alan.
Yeah, it drops
Quite a big
into
part.
3 parts.
Yeah, do you know what that's called?
Separation.
Staging.
Staging.
So stages. Come on, computer. Also, a bit of signposting. If you want to know a bit more about the science behind it, a chap called Tsiolkovsky, Russian. He actually came up with a rocket equation in 1903.
The Americans need to.
So the Saturn V, as you said, it drops bits off. So this fuel is spent, doesn't need these engines anymore, and it can just jettison that stage to lose weight. So it gets lighter and lighter and lighter as it goes up and up. So the Saturn V burns 20 tons of fuel per second at launch. And at takeoff, 6.5 million pounds of weight on the launch pad, with about 7.5 million pounds of thrust from these F1 engines. Anyone know who that chap is there?
Oh, was that the German?
Von Braun.
Yeah.
Yeah, von Braun. Yeah, so made the V2 bomb for the Nazis. Americans stole him and got him to work on the Apollo program. So 5 F1 engines on the first stage here. So it's 3 stages, and then further on I won't go on about the flight too much, but the lander was in a separate part of the top stage there, the 3rd stage. So 7.5 million pounds of thrust, 400 elephants sat on each chest. Speed. So we've exhausted most of our fuel. We've got to orbit. We're looking a bit like this. We shut our engines down. So why don't we just fall back to Earth?
Gravity.
Gravity is a thing, isn't it? So what keeps it up there? Momentum. Okay,
No.
so another volunteer that hasn't taken part yet. Tim,
Yeah.
do you want to be my swinger?
Hey!
So, if you just hold the end of that string, just swing the rocket round just nice and slowly. Okay, so it's not really getting up, is it? So we need speed and momentum to be able to keep going, don't we? So if you spin it a little bit faster, a little bit higher,
Actually, I'm going to go the other way.
go over your head, don't let it go. So what's happening here? So we've got momentum. Why isn't it just flying off in a straight line?
Got a string.
Got a string. So what's the string in relation to a rocket going around the Earth? Gravity. So gravity is essentially steering it around in a circle. So in space, there's no air resistance, so it can keep going and going and going forever and ever and ever. That's a diagram from back in the Newton days. So he theorised that if he has a cannon on top of a high mountain, fires it as fast as he can, eventually, if you're given the right speed, you'll go right around the Earth before it hits you on the back. Anyone know what the speed is to achieve orbit? 17,500 miles per hour. So the International Space Station, satellites in orbit, that's the speed generally that they're going at. So how do we get to the moon? How do we leave orbit? What do we need to do?
Go faster.
Go faster, yeah. So, where's my video? So, 17,500 miles an hour, we're in equilibrium. We want to go faster than that. We can leave orbit and shoot off to the moon. 25,000 miles an hour is the speed that you need to go to be able to do that. So imagine that string stretching out to the moon. So this is the orbital sort of trajectory that the rocket went. So it went round the Earth 1.5 times, sped up about here, and they're aiming to where the moon is going to be. It's called translunar lunar injection. So it's called a free return trajectory. So if anything went wrong, all they need to do is just stay on board. It will spin around the moon and then come back. So how do you work that out? There's an incredible amount of maths involved. There was 400,000 people that worked on the Apollo program at its height, and they actually invented new maths to be able to figure this out. This was all before the days of computers. If you're interested in that, there's a really good Netflix, I think, film called Hidden Figures about the women that
It's
were
really
involved
good,
in
yeah, very
doing
good,
that. Yeah, really good film. So, quick recap. So we talked about the sheer size of the rocket and why it needs to be so big, how much fuel we need because it's so far away, and how fast we need to go to get there. That thrust to weight, some of the design elements I might have skipped over, so like the honeycomb structure in the new metal alloys that they developed, the 3 stages to lose weight on its journey up into space, and the new F1 rocket engines developed by Von Braun on the first stage. I've got a quick quiz now. If you want to get your phones out, scan that QR code. Hopefully that all works. Right, I'm trying to find one here. Okay, everyone got it?
Sorry.
What show responses? Show results.
You need the QR code again.
Yeah.
No problem.
Thank you.
Okay, Alan, bring it down. So just waiting on you, Tim. Okay.
Are we going?
Yep, go, go, go.
Go, go, go. Oh. Ah. To write it down. Oh, bloody hell. Oh, dear. I'll listen to them.
We've got question 4, right?
Yeah. That's because most of us wrote that one down.
Is that the
At the
truth?
start, yeah.
Challenges.
Nice. Well done, Brendan.
Dan can still catch up.
Yeah. Pressure's on.
Oh, I knew this one. But no, I don't. That was a guess.
Cool, done, well done. So, excellent. So, who is the winner then? Brendan, well done, 89%, followed close behind with Danny and Tim. So, any questions?
Nope.
No, great. I think that's a good indication. Right, thanks very much.
Cheers, mate.